Give me that cheddar, we getting Rico. Big money rolls like burritos. Give me that.
All right. So far we've talked about voltage divider and current dividers with only two resistors. If I had a voltage divider that had multiple resistors, something like this, we've got R1, 2, 3, so forth, down to R sub n, and the voltage source connected across that. Then if I wanted to know the voltage across any one of those resistors, let's call it the j'th resistor, then the voltage across that is R sub j, whatever that happens to be, divided by the equivalent resistance times the voltage source. So R sub j over Req, that is the fraction of the voltage source that is across resistor j. Now, in this case, Req is just the sum of all of the resistors because these resistors are in series for a voltage divider. So Req is equal to the sum of the individual resistors where I is equal to 1 to n. Now, for a current divider, we can come up with a similar relationship here. So let's say we have a current divider that looks maybe something like this. So here's the current source over here that we want to divide between all of these resistors, and I'll label them 1, 2, 3, 4, all the way to R sub n. Now, if you want to know the current that's going through the j'th resistor, then I sub j is equal to Req over R sub j times I sub s. So the thing that's in the square brackets here is the fraction of I sub s that is across through the j'th resistor. And in this case, Req is given by this relationship, where I is equal to 1 to n. Now, if you look at this, when we had two resistors, you may recall that let's say I across the first resistor, I1, that was given by R2 over R1 plus R2 times I sub s, like that. So if we just had two resistors, in other words, no more than two, like that, then this is the relationship to find the current through that first resistor here. And you'll look at that and you say, well, that doesn't make sense. But if you just follow through here, for example, multiply this by 1. You know if you multiply by 1, you don't change anything. So let's take R2 over R1 plus R2, multiply by R1 over R1, which is just 1, times I sub s. And now you can see that we can put the R1 over here. So we have R1, R2 over R1 plus R2 over R1 times I sub s, like that. Well, what is this right here? Well, that's just product over sum for two resistors that are in parallel. So this really is Req divided by R1 times I sub s. And it works that way for, two resistors. It works that way for multiple resistors like this. So these two relationships are really the more general expressions for voltages and currents, for voltage and current dividers. Let's draw the traditional two resistor circuit here with two voltages divided. So V sub s is divided V1 and V2 across these two resistors. So let's call that one R1 and this one's R2 here. Now, we know the voltage V2 is going to be R2 over R1 plus R2 times V sub s. What's in the square brackets here is the fraction of V sub s that is divided across V2. Okay, now so far everything we've talked about has assumed that there's not actually a load hooked up to that voltage. In other words, if I were to tie a wire on there and bring a wire on out here, and I were to hook up something across this voltage here. The voltage from that point to that point, let's call that terminal A and this is terminal B, the voltage across those two terminals is V2. But if I want to connect this to something that's going to run, an example we gave previously is that maybe V sub S is 12 volts, but I just want 5 volts for V2. Well, whatever my 5-volt device is, I would connect it across these two terminals. Well, everything has resistance, so your 5-volt device may have a resistance of its own. So we can model that this way. And since it is since it is connected to the second resistor here to get the V2 voltage, this is the load. So this is R sub L. So a load resistor is just the resistance of the thing that's connected up across the V2 here. Now that's connected, so let's draw the lines there. And now you'll see that V2 has actually changed, because no longer is the resistance here just R2, but now I have a second resistance that's in parallel with R2. And the load affects the total resistance here, and therefore the load is also going to affect what V2 is. So if you were to put these two resistors together, this is still R1, but now this is R equivalent. And you still have V1 perhaps across that. Well, not even that. Well, let's just ignore V1 for right now. But the question is, what is this voltage here? Okay, well, the voltage, let's call that V output across that, because it's no longer V2. V output is going to be Req over R1 plus Req times V sub S. All right, so what's in the square brackets there, again, is the fraction of V sub S that is on the output voltage now. Okay, well, this Req is R2 times R sub L over R2 plus R sub L. So it's just the equivalent resistance when you combine these two, which are in parallel with each other. So this is not necessarily, this in the square brackets here is not necessarily the same thing as in the square brackets up here. In fact, it's not. If R sub L is any value, it's going to not be exactly the same. So by adding a load across your voltage source here, if by your V2, by adding a load across your V2, then you've literally changed the value of V2 to become this. Let me show you something. It is possible, if you select your R1 and your R2s wisely, to have a voltage that comes off of this that is very close to what V2 was originally. If you recall, in our example where we had a 12-volt source and we wanted 5 volts here, we said that R1 and R2 had to be a certain ratio. And that ratio for our example was we had a 12-volt source, we wanted 5 volts across V2, so the ratio of R2 to R1 had to be 5 over 7. But there are infinite combinations of R1 and R2 that will give us this ratio. For any R1 value you can think of, you can compute the R2 value based upon this ratio. So there are infinite combinations that will allow for this ratio then. But that means you could choose R1 and R2 to be very small, or you could choose R1 and R2 to be very large. Well, there is a way to pick R1 and R2 so that this ratio, so that your output voltage is very close to what you could compute using the divider equations for V2 right here. And let me show you how that comes about. The output voltage is given by this equation. That's nothing but me rewriting the equation that you just saw. And we know that Req is... So I'm going to take this and I'm going to substitute it in for each of these. Well, Req is... So this is the top Req multiplied by... So there's REQ, and here is REQ. Now I'm going to find a common denominator for this bottom part of the fraction here so that we can clean this up a little bit. That's nothing but rewriting this. And now I could put all of that over the common denominator of R2 plus RL, but it's going to be on bottom, so I'm going to put it on top. And now that reduces to this. Okay, let's take it another step farther. And now what I'm going to do is I'm going to factor out an R sub L from down here. So you see what I did there? I just factored out this R sub L. And by doing that, I see there's an R sub L term in all of these, so R sub L will cancel here as well. And now we're left with this. Now look at this equation right here, and you'll notice it looks an awful lot like V2. These two equations, this one and the one in the box here, you'll notice that V output is very close to what V2 is. The difference between V2 and V output is this term that's in the parenthesis right here. So if the term that's in the parenthesis right here, if that went away, then V2 and V output would be the same. Okay, well, when does that go away? Well, if you look at it, it never truly goes away, but you could reduce it down. It is this term right here, the R2 over RL. If we can reduce that down so that it is very, very small, then V output becomes very close to V2. So notice as R sub L goes to infinity, so R sub L gets very, very large, then what happens? Well, V output becomes V2 in that case. Okay, but what if we can't go to infinity, but what if we just let R sub L be much, much larger than R2? Then in that case, V output becomes very close to V2. So if we pick R sub L to be very large compared to R2, then V output will be very close to V2. Recall, we have infinite combinations for this ratio that we can pick. So we can pick very small values or very large values. As long as we keep the ratio, then we will have 5 volts for V2 from our 12 volt source. All right, well, as long as we are able to pick anything for 1 and 2, as long as we keep the ratio the same, then for our original drawing here, if we pick R sub L to be very large, and it turns out to be very large compared to R2, then V2 is going to be very close to the V output. So if we pick the ratio in such a way so that these resistors here, especially R2, is very small compared to R sub L, then problem solved. We can use this equation then to approximate what the output is going to be across resistor 2. So that's the point. When you add a load to a network, like a divider network, like this one here, when you add a load to a voltage divider, it changes the entire system. However, if you choose wisely for your ratio here, you can make it so that it approximates this, which is nice. Okay. Now, that may be important. That may be a good test question in the future, but it's probably more important to people that are in the labs. I want to talk about one more thing here. I want to talk about Wheatstone bridges. A Wheatstone bridge is a device that you can use to measure an unknown resistance, and it can do it at a fairly high precision. A bridge circuit is a circuit that literally joins two sides. So if you have resistors on the right side, resistors on the left side, and you put some kind of bridge between them, like another resistor between them, then that's a bridge circuit. That's what it's called. So you can draw that a number of ways. Let me show you one way. All right, so here I have resistors going down one side, here I have resistors going down the other side, and now I'm going to put something in the middle of these two to join them together. And the thing I'm going to put here is a galvanometer. A galvanometer, spelled... galvanometer is a device that measures some current flow. So you can think of this as being a needle, and if the current is going to the right, the needle may go over in this direction. If the current's going to the left, then the needle may go over into this direction. And it's calibrated in such a way that how far the deflection is determines how much current's going through it. It's proportional to how much current. So that's what a galvanometer is, a device that measures current flow there. And so if there is a current between that point and that point, let's label those 2 points. Let's call that point A and this point B. So if there is a current between A and B, then it will register on the galvanometer. Now, there will only be a current between A and B if A and B have a potential difference between them. So if there is a voltage between A and B that is not zero, then some deflection will be measured on the galvanometer. Okay, well, let's label our resistors here. This is resistor 1. This is resistor 2. Let's call this one over here resistor 3. And for our purposes, resistor 3 is going to end up being a variable resistor. And then this is an unknown resistor. We don't know what that is, so we don't know what its value is, so we'll just call it resistor X. According to what we know about KCL and KVL, if the galvanometer reads 0, then there is no current flow from A to B. And that means that the voltage at point A is equal to the voltage at point B. And if the voltage at point A is equal to the voltage at point B, so let's say if that, then we can say this: the voltage across resistor 1 is equal to the voltage across resistor 2. Now you might say, why is that the case? Well, up here, both resistor 1 and resistor 2 are joined together. So the top part of R1 and R2 is at the same voltage. And if there is no potential difference between A and B, so voltage A is equal to voltage B, then the voltage down here is also equal. So whatever the voltage is between the top and A for resistor 1, it's going to be the same between the top and B for resistor 2. So the voltage at 1 is equal to the voltage at 2. That only applies if there's no current, no potential difference between points A and B. And we could say this: the same thing would apply down here. Voltage 3 is going to be equal to the voltage across X, resistor X here. So if that's the case, then the currents here are going to look like this. Let's say we've got a current going down this way, and that's current 1. We'll say we've got a current going this way. We'll call that current 3. The current going this way, we'll call that current 2. And then the current here is I sub X. Now, if there is no current going from A to B or B to A for that matter, then I1 is equal to I3. In other words, the current coming down this way, none of it splits off and goes through the galvanometer. It all goes down here. So it should be obvious then, if there's no current going from A to B, that these two currents are just equal to each other. And we could say the same thing about the other side, that I2 is equal to I sub X. Okay, since there's no potential difference from A to B, then we can say V sub A is equal to V sub B. V1 is equal to V2. V3 is equal to V sub X. The currents I1 and I3 are equal, and the currents I2 and I sub X are equal. Well, if VA and VB are equal, then we could write this. This says V3, remember V equals IR, so this is I3 times R3 is equal to I sub X times V sub X. So this is a restatement of this here, that V3 is equal to Vx. We've just written it using Ohm's law. We could also say the same thing about V1 and V2 then. that I1R1 is equal to I2R2, like that. All right, well, since that's the case, what we can do is I'm going to substitute in these equations into here. So substituting in for I1, this becomes I1R3 is equal to I sub x is I2 R sub x. And of course, we'll just rewrite this bottom one. I1 R1 is equal to I2 R2, like that. Okay, now I'm going to take the ratio of these two equations. In other words, I'm going to divide the two equations. And whenever I do that, I end up with this. You'll notice the i's cancel on both sides. So I end up with R3 over R1 is equal to R sub x over R2. Or if I solve for R sub x is equal to R2 over R1 times R3. Here I have an equation then that allows me to determine what R sub x is as long as I know the ratio R2 to R1 and the value for R3 as well. So a Wheatstone bridge allows you to do this. So here's what normally happens. So usually this ratio of R1 to R2 is known. But R3 is a variable resistor. And the way that you draw a variable resistor is you just take a resistor and you put an arrow through it like that. So that's an adjustable resistance value. So R3 is adjusted then until there is no more current flowing through the galvanometer. So R1 and R2 are known and chosen. R3 is then dialed until the galvanometer shows that there's no current flowing from A to B. At that point, you know that V sub A is equal to V sub B. And then, if that's the case, then you can use this equation right here to determine what this unknown resistance is. Well, you might say you could just use a digital multimeter. That would be true. That will work. But it will not allow you to have the precision that you can get with a Wheatstone bridge circuit. So using the Wheatstone bridge in lab, nevertheless, this is an introduction to a type of circuit that you will see repeatedly, a bridge circuit. Now, let me redraw a Wheatstone bridge. The galvanometer itself has some internal resistance to it, which we could model here as just that. So this is R sub M, where M stands for meter. So this is the resistance, the internal resistance of the meter. Now, the reason I wanted to redraw this is because I want you to look at that and tell me, do you spot anything that is in series or parallel? Is R1 and R2, are those in parallel with each other? Are they in series with each other? No, they're not. There's nothing here that's in series or parallel with anything else. The reason R1 and R2 are not in parallel is because in order for something to be in parallel, their tops and their bottoms must really be electrically connected to each other. And since there's the meter between these two, that's a resistance, then those two right there are not in parallel with each other. So if I wanted to use circuit simplification and series parallel reduction to solve this type of circuit, I would not be able to do it. You cannot reduce this down using series parallel reduction because there's nothing in series and nothing in parallel. So what do you have to do? Well, you have to rely upon another technique. And that technique comes with multiple names. It can be Y to delta, or conversely, delta to Y. It can also be pi to T. Sometimes it is called a star delta transform. All of those mean the same thing. They are techniques to reduce this type of circuit down when you cannot use series parallel reduction. This is what we're going to talk about in the next video. We'll do this next time, and Bob's your uncle.
Big money rolls like burritos. Give me that hot sauce, no pico. Give me that.